In part 6 of our review chapter, it will be everyone's favorite unit and sometimes the most misunderstood two topics in your high school math career. We're going to focus on logarithmic and exponential functions. And if you've been alive during this pandemic age, you have seen why exponential growth is such an important factor when it comes to a lot of bad stuff going on in the world. So let's talk about first exponential functions. Then we'll talk about their inverses, which are logs, and their basic properties. And many of you guys are really good at exponential functions. So an exponential function is a function of the form f of x equals b to the x, where we call b the base and the variable is in the exponent. Do note that the base has to be greater than 0, and if it's equal to 1, then it is just itself over and over and over again, so it's not an interesting function. Therefore, we restrict the domain to be the base to be positive and not 1. So with that, we can look at some basic properties of exponential functions. First of all, b of x, which means the y values or the outputs or the range for an exponential function, will always be positive for all x. Now, this doesn't bring into shifts moving the graph down, but in general, if you have an exponential function, it is a positive number generator. The range for an exponential function will be all positive reals. So I will just rewrite this, all positive real numbers. And as I say both in class and in these videos, mathematicians are inherently lazy, so they're going to look to find the shortest way possible to write something. So if you see this little symbol here, that just means the positive real numbers. Third property, if our base is greater than 1, we call that exponential growth. And it's growing in that pattern. Likewise, if our base is a fraction, so between 0 and 1, but not 0 and not 1, we call that exponential decay. You'll see this in chemistry classes or biology when you're talking about half-life, and it is the reflection over the y-axis. Exponential growth, exponential decay. So if you switch an exponential function to its inverse, so what I like to write is a equals b to the e, or let's put this in the right order. If you have an exponential function, base, exponent equals answer. To find its inverse, what you do is you remember your bay. So the base will be log base b. The answer is the input, because this is the input, and this answer is your output. Inverses switch the output of the original function with the input. So why I say bay is base, answer, exponent, base, answer, exponent. They're all the same pieces, they're just in different order. The definition of a logarithmic function is log base b of x is the power on b that gives the answer x. So some basic properties that we can look at here, which you should know. If we say log base 2 of 8, that's the same thing as saying 2 to what power gives me 8. So log base 2 of 8 is equal to 3. So you could easily say 8 is 2 cubed, and so the answer, if you were evaluating these, is 3. Second one, log base 10 of 1. 10 to what power gives you 1? 10 to what power gives you 1? Well, anything to this power gives you 1, and that's 0. And the third one, log base 3 of 1/9. 3 to what power gives you 1/9? Well, if we remember our properties of exponents, if we're trying to get like bases, we could say 9 is 9 to the negative first, and 9 is 3 squared, so that would be 3 to the negative second. So if our exponents are equal, then our answers are the exponent. With common logs, since all of our numbers that we deal with in general are base 10, we write the common log as log base 10. The 10 is implied. We just write log x for whatever number. For the natural log, that is log base e. And you can find that on your calculator with ln of x. E, if you forgot, is Euler's number, and it is 2.71, just like non-repeating, infinite, non-terminating decimal, just like pi. Properties of logs. Well, if you know what the properties of an exponential function are, then we just switch the domain and the range. So the range of an exponential function will give us the domain of a log. So the domain of a log is any number that's positive. The range is all reals. What the graph of a logarithmic function looks like is we have a vertical asymptote because we need to be a positive number. If I plug in 1, I get 0 out, and then it kind of looks like an exponential function reflected over the line y equals x. Now, what are the laws and then some examples of logarithms? This is just a fancy way of writing our properties of exponents we did in part 1. The ones where you're like, this is really easy, Mr. Swenson. I know what I'm doing here. If you know your properties of exponents, you intrinsically know the properties for logs. So log of 1. If we write log base b of 1, that will always be equal to 0. Likewise, if we have the identity log base b of b, that is equal to 1, because b to the first is equal to 1. Base, answer, exponent. If we multiply like bases, or we have multiplication inside a log, we can separate that out to addition. Because when we multiply like bases, we add the exponents. So this just turns into the sum of 2 logs. If we're looking for an example here, just zoom in. If I had log base 2 of 32, I could write that as 2 times 16. Now I have a product. Well, log base 2 of 2 plus log base 2 of 16. Well, I know from the property above that log base 2 of 2 is 1, and 2 to the 4th power is 16. So really, this problem just boils down to 1 plus 4, which is 16. If we are dividing, when we're dividing like bases, when our properties of exponents, we subtract the exponents. So when we have division inside a log, we can separate that out into subtraction of those 2 division problems. So log base b of y. An example of this property would be, let's say we had log base 2 of 4. You could write this as log base 2 of 32 minus log base 2 of 8. 32 divided by 8 is 4. These are 2 equivalent representations. So when we have division, we can subtract. Other properties. If I have a function or a fraction inside a log, Let's say we have log base b of 1 over x. Just like we did with exponents, we moved it up or got rid of the fraction and turned it into a negative exponent. Likewise, because 1 over x is just x to the negative first, I can put the negative sign in front of my log. Subsequently, if you have something raised to a power, let's say n, then n, if you think about it, just like we did with powers raised to a power, this is just n copies of x multiplied together. This is x times x times x. And we have n of these. Well, what we said before is if we have multiplication inside, we just turn that into addition. So we're adding x n times, which means n log base b of x. The way I try to tell my students, if you have a log and you have something raised to an exponent, just take that exponent, move it in front. That's all we're doing. Last one, which is used when you need to do something fancy, but we won't see this a whole lot in this course, is the change of base formula. So the way I remember this is if we want a different base, let's say we want the common log or we want natural log, let's say ln or log base 10. Well, the base always go on the bottom because you sit on your base. So we turn this into a division problem, and it would be either ln of x divided by ln of b, or we could write this as log x over log b. It could be whatever base you want. This will come in handy when we get to integrals and we have a complicated thing that we need to separate out. We love using logs because it allows us to separate out complicated expressions. So we need to first understand how to either expand or contract these two. And the instruction you'll see is just simplify. So simplifying a log. Anytime we see addition, it's going to turn into multiplication. So we'll have log base 2 of 5 parentheses x squared minus 1 minus log base 2 of x minus 1. Subtraction, when we have like bases, will turn into division. So we would have log base 2 of 5, and I'm just going to break that difference of squares into conjugate pairs. And now we have one log with a quotient and a product on the top. And now we can simplify this fraction, and this just turns into log base 2 of 5 parentheses x plus 1. Now here's the really cool thing. Let's say you wanted to do this in a slightly different way. So I'm just going to shrink this down. That answer all worked, but I'm going to switch this to purple. Let's say you wanted to expand this out first and subtract everything as a base 2. So we're good right there. So you could have log base 2 of 5 plus, if you think about x squared minus 1, it's technically x plus 1, x minus 1 multiplied together. You could have log base 2 of x plus 1. You could have plus log base 2 of x minus 1. Take away log base 2 of x minus 1. Now, this and this are the same exact quantity, one copy of each, so they cancel each other out, which leaves us simply with log base 2 of 5 x plus 1, since they're all multiplied together. That's the neat thing when you are combining these terms, is it doesn't really matter what order of the properties you go in, whether you combine everything first, then simplify. So you could say this final answer would be log base 2 of 5x plus 5. As long as you apply the properties in the appropriate manner, you're good. Similarly, log base 10 of 1 over 10 to the x. Well, here we have our reciprocal function. So I'm just going to write log because log base 10. Anything in the denominator, we can just move up with a negative exponent. If we have our negative exponent here, let's just grab that negative x. Well, we have a exponent. We can just slide that right out front. And now we have log base 10 of 10, which is just 1. So our final answer, if we're just simplifying that, is negative x times 1 or negative x. Simple, easy, efficient, once you understand what you're doing. If you have any questions on simplifying logs, ask them when we get into class. I do not want you guys to do these problems without knowing what you're doing, because we need to know what we're doing with logs. Last bit, if we are solving a logarithmic equation, the technique we're going to use, I'm going to switch back to black, we are going to convert between logs and exponential form, logarithmic form and exponential form. And then we're going to apply our properties of logs or our properties of exponents to set either the exponents equal or get the bases equal for the logs. So what do I mean by that? First off, we have log base 3 equal to 2. So in order to combine the terms on the left-hand side, addition turns into multiplication. So I have log base 3 of 3x parentheses x minus 2 equals 2. And now I have base, exponent, answer. So I have 3 to the second power equals 3x squared minus 6x. That's just distributing the 3x to both terms. 3 squared is 9. If I get everything over onto the right side, I have 0 equals 3x squared minus 6x minus 9. All of these are divisible by 3, so I'm left with x squared minus 2x minus 3 is equal to 0. And then I can just factor this. So I have, just go up here, 0 equals x minus 3, x plus 1. Set both of those equal to 0, so I have x equals 3 and x equals negative 1. Great. The only problem is, after we solve this, we need to check our answers. Because, as we said at the beginning of this video, the domain of a log, the domain is x is greater than 0. So if one of our original problems, our original setup, gives us a negative value, then we're no good. Doesn't work, so that answer is not a solution. So if we check out 3, 3 times 3 is positive, that works. 3 minus 2 is positive, that works. So x equals 3 is a solution. If I plug in negative 1 into our first log, I have 3 times negative 1, that's negative. So negative 1, although it factors out nicely, is not a solution to the problem. We'll do 2 more of these, and then I'll give you the last one to solve on your own. So we have 2 log 2x plus 1, 2x plus 4 minus this equals 2. First things first, anything that's in front, I need to move up. So I would have log base 2x plus 1 of 2x plus 4 squared. Subtraction turns into division, so over 4 equals 2. Now I'm going to base answer exponent. So base answer exponent, B-A-E. So I have 2x plus 1 to the second power equals 2x plus 4 squared. Well, if I have squared terms on either side, I'm going to do a sneaky little shortcut. Let's make sure that Mr. Swenson writes all of the terms. Square root, square root. Notice one of these sides I'd have absolute value. So I'm going to have 2 possible answers. So let's just do this in blue, let's say. So 2x plus 1 is equal to 2x plus 4 over the absolute value of 2. Or another way of writing the denominator is plus or minus 2. Now, I did a quick shortcut. If you need to, why do we have 2 possible solutions here? Think about that. So our first one, we would have 2x plus 1 is equal to 2x plus 4 over 2. Our second solution would be the same. 2x plus 1 is equal to 2x plus 4 over negative 2. Now I'm just going to do a quick multiplication. So I'd have 4x plus 2 is equal to 2x plus 4. 2x is equal to 1 because we have 2x is equal to 2. That's one solution. Let's make sure we don't box that in just yet. Our second solution would be negative 4x minus 2 is equal to 2x plus 4. Subtract 4, I get negative 6. Add 4, I get 6. So I have x equals negative 1. Again, we have to check our solutions to the original problem. Now we're plugging into both the base and the problem. So if I plug in 1, I would have 2 times 1 plus 1, 3. That's good. If I had 2 times 1, which is 2 plus 6, that's good. So positive 1 works. If I plug in negative 1, I have 2 times negative 1 is negative 2 plus 1 is negative 1. I can't have a negative base. Don't work from there any further. Last two are exponential functions. I can go two ways. Log both sides, or switched it to logarithmic form, or get the exponents the same. I'm going to show you how to do it just by switching it to logarithmic form. So we'd have log base 2, base exponent answer, base answer equals exponent. Now we know log base 2 of 16 is equal to 4. So we have x plus 4 is equal to 4, or x equals 0. That is not the only way you can do this problem. If you wanted to, you could say 2 to the x plus 4 is equal to 2 to the 4th power. And now we set the exponents equal. So we have x plus 4 is equal to 4, or x equals 0. Either of those work. Notice also, any solution here we don't have to check because the original is an exponential function. And I know I said I'd save D for you, but I really just want to show you this one because this is going to probably trip up some people. First, to combine things, I would have 4 and 2 are not like bases. So I first need to say 4 is 2 squared times 2 to the x minus 2 is equal to, let's count by powers of 2. We have 2, 4, 8, that's the third. 4th power is 16. 5th power is 32. 6th power is 64. 7th power is 128. These are all powers of 2. 1, 2, 3, 4, 5, 6, 7. So we have that equal to 2 to the 7th power. When I multiply like bases, I add the exponents. So this would be 2 to the 2x plus x minus 2 equals 2 to the 7th. And now 2 plus 1 is 3. 3x minus 2. I just have 3x minus 2 equals 7. 3x equals 9. X equals 3. That is not involving any logs. You could also, once you get the bases the same and you get it 2 to the 3x minus 2 is equal to 2 to the 7th. If I'm just doing this work a slightly different way, you could also then, let's just move this slightly over so I can write it, take the log of both sides. And by taking the log of both sides, I can now move the exponent in front. 3x minus 2 log base 2 is equal to 7 log base 2. The log base 2's go away because they're the same, just multiplied out. And that's what gives me 3x minus 2 equals 7, or x is equal to 3. I know this video was a little longer, but I wanted to make sure that we incorporated all of the properties that you need to know in order to analyze exponential functions and logs. This takes care of part 6. The next video, we will be analyzing trigonometric functions. So all of the things that you kind of learned, but not really last year at the end of the year, we're going to really get good at. So we'll practice a few different ways in class to remember our unit circle and graphing trigonometric functions. See you in the next ones, Falcons.